A rocket is a vehicle that moves by expelling mass at high speed in one direction to produce motion in the opposite direction. This method of movement is called rocket propulsion. Unlike cars, ships, or airplanes, rockets do not rely on interaction with the ground, water, or surrounding air to move forward. Their motion is governed by fundamental physical laws and works in both Earth's atmosphere and the vacuum of space. The defining feature of a rocket is that it carries all the material it needs to generate thrust. This includes both the propellant that is expelled backward and, when combustion is involved, the oxidizer needed for the chemical reaction. Because rockets are self-contained systems, they can operate in environments where there is no oxygen and no medium to push against. Rocket motion is based on the conservation of momentum. When mass is ejected from the rocket at high velocity in one direction, the rocket experiences an equal and opposite change in momentum, causing it to accelerate in the other direction. This principle applies regardless of whether the rocket is in air, underwater, or in outer space. The presence or absence of air does not affect the fundamental mechanism of propulsion. A common misconception is that rockets need air to push against in order to move. In reality, the force that accelerates a rocket comes from the internal interaction between the rocket and the expelled exhaust. The exhaust gases exert pressure on the walls of the engine and are accelerated through a nozzle, producing thrust. This process functions independently of the surrounding environment. Rockets differ from aircraft in both design and operation. Aircraft generate lift and thrust by interacting with air using wings and propellers or jet engines. They require an atmosphere to fly. Rockets, by contrast, do not depend on aerodynamic lift for forward motion, although aerodynamic forces can affect them while they pass through an atmosphere. A rocket's ability to function in space makes it essential for launching satellites, spacecraft, and probes beyond Earth. The structure of a rocket is typically cylindrical, a shape chosen to withstand internal pressure efficiently and minimize aerodynamic drag during atmospheric flight. Inside the rocket are tanks or casings that store propellant, engines that convert chemical or other forms of energy into kinetic energy, and structural components that hold everything together under extreme stress. Even small increases in mass significantly affect performance, so rockets are designed to be as light as possible while remaining strong. Rockets can vary greatly in size and purpose. Small rockets may be only a few centimeters long and are used for signaling, hobby applications, or scientific instruments. Large orbital rockets can exceed 100 meters in height and weigh thousands of tons at launch. Despite these differences, all rockets operate according to the same physical principles. Not all rockets rely on chemical combustion. Some rockets use cold gas, where compressed gas is expelled without combustion. Others use electric propulsion, accelerating charged particles using electromagnetic fields. While these systems differ in efficiency, thrust level, and application, they all qualify as rockets because they produce motion by expelling mass. The performance of a rocket is primarily determined by how fast it can expel mass and how much mass it expels per unit time. Faster exhaust velocities generally result in higher efficiency, while higher mass flow rates produce greater thrust. These parameters define how quickly a rocket can accelerate and how much payload it can carry. A rocket is therefore best understood as a momentum exchange machine, rather than a device that pushes against its surroundings. Its ability to function in a vacuum is not an exception or special case, but a direct consequence of the physical laws that govern motion. This property is what makes rockets uniquely suited for spaceflight and exploration beyond Earth. Rocket motion is governed by classical mechanics, primarily the laws of motion formulated by Isaac Newton. Among these, Newton's third law of motion is the most directly responsible for how rockets generate thrust. This law states that for every action, there is an equal and opposite reaction. In the context of a rocket, the action is the expulsion of mass at high speed in one direction, This expelled mass carries momentum. Because the total momentum of a closed system must be conserved, the rocket itself must gain momentum in the opposite direction. The rocket's forward motion is therefore a direct result of momentum conservation, not of interaction with air or any external surface. Newton's first law, which describes inertia, explains why a rocket continues moving once it is in motion. If no external forces act on the rocket, it will continue traveling at a constant velocity in a straight line. In space, where drag is negligible, a rocket does not need continuous thrust to keep moving forward. Thrust is only required to change velocity, such as when accelerating, decelerating, or altering direction. Newton's second law relates force, mass, and acceleration. It states that force equals mass multiplied by acceleration. For rockets, this law explains why mass is such a critical factor in design. As a rocket burns propellant, its mass decreases. For a given amount of thrust, a lower mass results in higher acceleration. This is why rockets accelerate more rapidly later in flight, after much of their propellant has been consumed. The thrust produced by a rocket engine depends on two main factors: the mass flow rate of the exhaust and the velocity at which that exhaust is expelled. Thrust can be understood as the rate of change of momentum. Increasing exhaust velocity, or increasing the amount of mass expelled per second, increases thrust. Rocket engines are therefore designed to maximize exhaust velocity while managing structural and thermal limits. The rocket nozzle plays a key role in converting internal energy into directed momentum. Hot gases generated by combustion are initially at high pressure inside the engine. As these gases expand through the nozzle, pressure energy is converted into kinetic energy, accelerating the exhaust to extremely high speeds. The shape of the nozzle is carefully engineered to optimize this expansion process. A key mathematical relationship in rocketry is the rocket equation, which relates a rocket's change in velocity to the exhaust velocity and the ratio of initial mass to final mass. This equation shows that carrying more propellant allows for greater changes in velocity, but also that there are diminishing returns as more mass is added. This relationship is fundamental to understanding why rockets are staged and why launching payloads into orbit is so challenging. External forces such as gravity and aerodynamic drag also influence rocket motion, especially during launch from Earth. Gravity continuously pulls the rocket downward, reducing its upward acceleration. Drag opposes the rocket's motion through the atmosphere and depends on velocity, shape, and air density. Rocket trajectories are designed to minimize these losses while achieving the required speed and direction. The laws governing rocket motion apply equally in all environments. Whether a rocket is launched from Earth, operating in space, or maneuvering near another planet, the same principles of force, mass, acceleration, and momentum apply. Rockets do not behave differently in a vacuum because the laws of motion do not depend on the presence of air. In summary, rockets operate as direct demonstrations of Newtonian mechanics. Their motion is the predictable result of mass ejection, momentum conservation, and the relationship between force and acceleration. Understanding these laws provides a complete and accurate explanation of how rockets move, without the need for assumptions about external support or interaction with the surrounding environment. The history of rockets spans more than 1,000 years and reflects the gradual transition from simple reactive devices to complex space launch systems. The earliest known rockets appeared in China during the first millennium. These early rockets were based on gunpowder, a mixture of charcoal, sulfur, and potassium nitrate, initially developed for fireworks and ceremonial displays. Gunpowder rockets were later adapted for military use as weapons and signaling devices. By the 13th century, Chinese military forces were using rocket-like weapons such as fire arrows. These consisted of a tube filled with gunpowder attached to an arrow shaft. When ignited, the propellant expelled gas backward, pushing the device forward. Although inaccurate and limited in range, these early rockets demonstrated the basic principle of reaction propulsion. Knowledge of gunpowder and rocket weapons spread westward through trade routes and warfare, reaching the Middle East and Europe. In Europe, rockets remained primarily military curiosities for several centuries. During the 18th and early 19th centuries, more systematic development began. One notable example was the use of military rockets by British forces in India and later in Europe. These developments led to the creation of standardized rocket artillery, such as the Congreve rockets used by the British Army in the early 1800s. Despite improvements, these rockets were still unstable and less accurate than conventional artillery. Scientific understanding of rocket motion advanced significantly in the late 19th and early 20th centuries. The Russian scientist Konstantin Tsiolkovsky developed the theoretical foundations of spaceflight. He derived the rocket equation, which mathematically describes how a rocket's velocity depends on exhaust speed and mass ratio. Tsiolkovsky also proposed the use of liquid propellants in multi-stage rockets, concepts that would later become essential to space travel. In the United States, Robert H. Goddard conducted practical experiments that transformed rocketry from theory into engineering reality. In 1926, Goddard successfully launched the world's first liquid-fueled rocket. Liquid propellants allowed for greater control, higher efficiency, and longer burn times than solid propellants. Goddard also developed gyroscopic stabilization, steering systems, and fuel pumps, many of which are still fundamental to modern rockets. During the 1930s and 1940s, rocket development accelerated due to military interest. In Germany, engineers led by Wernher von Braun developed the V-2 rocket during World War II. The V-2 was the first human-made object to reach the edge of space, and the first large-scale liquid-fueled ballistic missile. It demonstrated that rockets could achieve high altitudes and long ranges, but it was developed as a weapon rather than a scientific tool. After World War II, rocket technology spread rapidly as scientists and engineers moved to other countries. Both the United States and the Soviet Union incorporated German rocket expertise into their own programs. This period marked the beginning of the Cold War space race. Rockets were now seen not only as weapons, but also as vehicles for exploration, communication, and national prestige. In 1957, the Soviet Union launched Sputnik 1 using a modified intercontinental ballistic missile. This event marked the beginning of the space age. It demonstrated that rockets could place objects into orbit around Earth. The success of Sputnik led to increased investment in rocket development worldwide and the establishment of civilian space agencies. The United States responded by creating NASA and accelerating its own launch vehicle programs. Throughout the 1960s, increasingly powerful rockets were developed to support human spaceflight. This culminated in the Saturn V, the largest operational rocket ever built, which carried astronauts to the moon during the Apollo program. From the late 20th century onward, rocket development expanded beyond government programs. Advances in materials, computing, and manufacturing enabled greater reliability and precision. In the 21st century, private companies introduced reusable rockets, reducing launch costs and increasing launch frequency. Despite these changes, modern rockets remain direct descendants of early gunpowder devices, governed by the same physical principles that have applied since the first reactive propulsion systems were invented. Reaching space and orbit requires enormous power because Earth's gravity creates a deep gravitational well that must be overcome or balanced by velocity. Any object at Earth's surface is constantly pulled toward the planet's center by gravitational force. To move upward, a rocket must produce thrust greater than its own weight. This alone requires significant force, even before accounting for other losses such as air resistance. Gravity does not end at a specific altitude. It weakens with distance but extends far into space. As a result, a rocket must continue expending energy, not only to lift itself off the ground, but also to keep accelerating long enough to achieve the speeds required for spaceflight. Simply reaching a high altitude is not sufficient. The rocket must also gain substantial horizontal velocity. To remain in orbit around Earth, an object must travel sideways fast enough that, as it falls toward the planet due to gravity, the surface curves away beneath it. This condition defines orbital motion. Near Earth, orbital velocity is approximately 7.8 kilometers per second. Achieving this speed requires a very large amount of kinetic energy, which must be supplied by the rocket's engines through propellant combustion. Escape velocity represents the minimum speed an object needs to break free from Earth's gravitational influence entirely, assuming no further propulsion. At Earth's surface, escape velocity is about 11.2 kilometers per second. Although most rockets do not reach this speed directly from launch, it illustrates the scale of energy involved. The kinetic energy required increases with the square of velocity, meaning that small increases in speed demand disproportionately large increases in energy. Rockets must also overcome gravity losses during ascent. While a rocket is climbing vertically, part of its thrust is spent merely counteracting gravity rather than increasing useful velocity. The longer a rocket spends ascending slowly, the more energy is lost to gravity. This is why rockets accelerate aggressively and gradually tilt over to gain horizontal speed as early as possible without excessive aerodynamic stress. Air resistance, or drag, further increases power requirements. As a rocket moves through the atmosphere, it experiences drag that depends on air density, velocity, and shape. Drag converts some of the rocket's energy into heat and turbulence, which does not contribute to reaching orbit, although drag decreases rapidly with altitude as the air thins. It is significant during the early phase of flight when the rocket is moving fastest through dense air. Another major factor is the mass of the rocket itself. Rockets must carry not only their payload, but also their engines, structure, and large quantities of propellant. Because fuel is heavy, a substantial portion of the rocket's launch mass is propellant used to lift other propellant. This creates a compounding effect where increasing required velocity demands exponentially more fuel, as described by the rocket equation. Chemical energy density also limits how much power can be generated. Chemical rockets rely on the energy released by breaking and forming molecular bonds. While this energy is large on human scales, it is modest compared to the gravitational and kinetic energy demands of orbital flight. As a result, rockets must burn large amounts of propellant at extremely high rates to produce sufficient thrust and exhaust velocity. The power output of a large launch rocket is enormous. At liftoff, major rockets generate power comparable to or exceeding that of large electrical power plants, but concentrated into a few minutes of operation. This power is released in a controlled manner through rocket engines, designed to withstand extreme temperatures, pressures, and mechanical loads. In summary, rockets require enormous power because they must lift heavy vehicles against constant gravity, overcome atmospheric drag, and accelerate to extremely high speeds. These demands arise from fundamental physical laws rather than technological inefficiency. The scale of power involved is a direct consequence of Earth's mass, size, and gravity, combined with the limits of chemical energy and the physics of motion. Rocket thrust is the force that propels a rocket forward by expelling mass backward at high speed. This force is generated entirely by the rocket engine and does not depend on the surrounding environment. Thrust arises from the transfer of momentum between the rocket and its exhaust, in accordance with the conservation of momentum. In a rocket engine, propellant is accelerated and expelled through a nozzle. As mass leaves the rocket in one direction, the rocket experiences an equal and opposite change in momentum, producing forward acceleration. This interaction occurs within the rocket system itself. The surrounding air, or lack of it, does not contribute to thrust generation. Thrust depends primarily on two physical quantities: the mass flow rate of the exhaust and the velocity at which that exhaust is expelled. Mass flow rate refers to how much propellant is expelled per second. Exhaust velocity refers to how fast that propellant leaves the engine. Increasing either quantity increases thrust, although practical limits exist due to engine materials, temperatures, and pressures. In chemical rockets, thrust begins with combustion. Fuel and oxidizer react inside a combustion chamber, releasing chemical energy in the form of heat. This heat raises the temperature and pressure of the reaction products, turning them into high-energy gas. The gas molecules move rapidly and collide with the walls of the chamber, creating pressure in all directions. The combustion chamber is designed to withstand extremely high pressures and temperatures, while the pressure inside pushes outward in all directions. The engine is shaped so that the only direction the gas can escape is through the nozzle. The walls of the chamber experience equal pressure forces that cancel out, while the nozzle provides a preferred exit path for the gas. The rocket nozzle is a critical component in thrust generation. Its purpose is to convert the thermal and pressure energy of the hot gas into directed kinetic energy. As the gas flows through the nozzle, it expands and accelerates. The nozzle's shape is carefully engineered so that the gas exits at very high speed, often several kilometers per second. The force on the rocket comes from two contributions. The first is the momentum of the exhaust leaving the nozzle. The second is the pressure difference between the exhaust at the nozzle exit and the surrounding environment. When exhaust pressure at the exit plane is higher than ambient pressure, it contributes additional force. In near-vacuum conditions, nozzle expansion can be optimized to maximize exhaust velocity. Thrust is produced continuously as long as mass is expelled. If the engine shuts down, thrust immediately drops to zero. Unlike engines that rely on lift or airflow, rockets do not generate sustained force without expelling mass. This is why rockets carry large amounts of propellant and operate for limited durations. The direction of thrust is determined by the orientation of the nozzle. By changing the nozzle's direction or redirecting exhaust flow, rockets can steer and control their motion. This steering does not change the basic thrust-producing mechanism, but alters the direction in which momentum is exchanged. Thrust is distinct from power, although the two are related. Power refers to how quickly energy is expended, while thrust refers to force. Rocket engines deliver extremely high power over short periods, converting chemical energy into kinetic energy of the exhaust. The efficiency of this conversion affects how much thrust is produced for a given amount of propellant. In summary, rocket thrust is the result of accelerating mass in one direction to produce force in the opposite direction. It arises from internal processes governed by momentum conservation, pressure, and energy conversion. The generation of thrust does not require air, external support, or interaction with the environment, making it effective in both atmospheric and vacuum conditions. Rocket propellants are the substances expelled by a rocket engine to produce thrust. In most rockets, propellant consists of two components: fuel and oxidizer. The fuel provides chemical energy, while the oxidizer supplies the oxygen or other reactive element required for combustion. Both are carried on board because rockets must operate in environments where atmospheric oxygen is unavailable. Fuel is the substance that releases energy when it reacts chemically. Common rocket fuels include liquid hydrogen, kerosene-based fuels, hydrazine derivatives, and solid polymer compounds. The choice of fuel depends on factors such as energy density, storage requirements, stability, and engine design. Different fuels release different amounts of energy per unit mass when burned. An oxidizer is required because combustion is a chemical reaction that needs an oxidizing agent. On Earth, Aircraft engines draw oxygen from the air, but rockets cannot rely on this because air becomes thin at high altitude and non-existent in space. Common oxidizers include liquid oxygen, nitrogen tetroxide, and ammonium perchlorate. The oxidizer enables the fuel to burn rapidly and release large amounts of energy in a controlled manner. The combination of fuel and oxidizer determines the performance of a rocket engine. One important measure is exhaust velocity, which reflects how efficiently the chemical energy of the propellant is converted into kinetic energy of the exhaust. Propellant combinations that produce lighter exhaust molecules generally achieve higher exhaust velocities, improving overall efficiency. Liquid propellants are stored in separate tanks and pumped into the combustion chamber, where they mix and ignite. This allows precise control over thrust by adjusting flow rates. Liquid systems can be throttled, shut down, and restarted, making them suitable for complex missions. However, they require complex plumbing, pumps, valves, and cooling systems. Solid propellants combine fuel and oxidizer into a single solid mixture. Once ignited, the propellant burns until it is exhausted and cannot easily be stopped or controlled. Solid rockets are mechanically simpler and can remain stored for long periods, but they offer less control during operation. Their burn rate is determined by the shape and composition of the propellant grain. Some rockets use hypergolic propellants, which ignite automatically upon contact between fuel and oxidizer. This property simplifies engine ignition and increases reliability, especially for spacecraft maneuvering systems. However, hypergolic propellants are often highly toxic and corrosive, requiring careful handling and containment. The amount of propellant carried by a rocket dominates its total mass at launch. In large orbital rockets, propellant typically accounts for the majority of the vehicle's weight. This is a direct consequence of the energy required to reach orbit and the limitations imposed by chemical energy density. A significant portion of the propellant is used to lift the remaining propellant. Propellant choice also affects storage conditions. Some propellants must be kept at extremely low temperatures to remain liquid, while others can be stored at room temperature. Cryogenic propellants offer high performance but introduce challenges such as boil-off and insulation requirements. Storable propellants simplify operations but may reduce efficiency. Not all rockets rely on chemical propellants. Some systems expel inert gases or ionized particles using electrical or mechanical energy. These alternatives produce much lower thrust, but can operate for long durations with high efficiency. Regardless of the energy source, all rocket propellants serve the same fundamental role, providing mass that can be accelerated and expelled to generate thrust. In summary, rocket propellants are carefully chosen combinations of fuel and oxidizer that enable controlled energy release and high-speed mass ejection. Their chemical and physical properties determine thrust, efficiency, controllability, and mission capability. The requirement to carry both fuel and oxidizer is what allows rockets to operate independently of their environment and reach space. Rocket engines are commonly classified by how their propellants are stored and burned. Two of the most widely used types are solid rocket engines and liquid rocket engines. Both operate on the same fundamental physical principles, but differ significantly in design, performance, controllability, and operational complexity. Solid rocket engines use propellant in a solid form, where fuel and oxidizer are mixed together into a single hardened material. This propellant is cast into a specific shape inside the engine casing. When ignited, the surface of the solid propellant burns and produces hot gases that are expelled through a nozzle to generate thrust. The burn continues until all usable propellant is consumed. Liquid rocket engines store fuel and oxidizer in separate tanks. These liquids are fed into a combustion chamber using pumps or pressure systems, where they mix, ignite, and burn. The resulting high-pressure gases are directed through a nozzle to produce thrust. Because propellant flow can be controlled, liquid engines allow for adjustable thrust levels and precise timing. One of the main advantages of solid rocket engines is mechanical simplicity. They have relatively few moving parts and do not require complex pumps or valves. This simplicity makes them robust and reliable. Solid rockets can be stored for long periods in a ready-to-use state, which is why they are commonly used in military applications and as boosters for launch vehicles. A key limitation of solid rocket engines is the lack of control once ignition occurs. After ignition, the engine burns until the propellant is exhausted. Thrust cannot be easily throttled, shut down, or restarted. The thrust profile is determined by the internal shape of the propellant grain, which controls how much surface area is burning at any given time. Liquid rocket engines offer much greater control. By regulating propellant flow rates, engineers can throttle thrust, shut down the engine, or restart it multiple times. This controllability is essential for missions that require precise maneuvers, orbital insertion, or landing operations. Liquid engines are therefore commonly used for main propulsion and upper stages. The complexity of liquid engines introduces challenges. High-performance liquid engines require turbopumps that operate at extreme speeds and pressures. These components must handle cryogenic temperatures, intense heat, and mechanical stress. This increases development cost, manufacturing difficulty, and the potential for failure compared to solid engines. Performance differences between solid and liquid engines are often measured in terms of efficiency and thrust-to-weight ratio. Liquid engines generally achieve higher efficiency because they can optimize combustion conditions and exhaust expansion. Solid engines can produce very high thrust for their size, making them useful for initial liftoff assistance, but they are less efficient overall. Safety considerations also differ. Solid propellants are stable under normal conditions, but contain both fuel and oxidizer in close contact, which can pose risks if damaged or improperly handled. Liquid propellants are stored separately, reducing some risks, but many liquid fuels and oxidizers are toxic, corrosive, or highly reactive, requiring careful handling and safety systems. Thermal management is another distinction. In liquid engines, fuel or oxidizer is often circulated around the combustion chamber and nozzle to absorb heat before being burned, a process known as regenerative cooling. Solid engines rely primarily on insulating materials and ablative liners to protect the casing from heat. In practical rocket design, solid and liquid engines are often combined. Large launch vehicles may use solid boosters to provide high thrust at liftoff, and liquid engines for sustained, controllable propulsion later in flight. This hybrid use leverages the strengths of both engine types. In summary, solid and liquid rocket engines represent different engineering trade-offs. Solid engines offer simplicity, reliability, and high thrust with limited control. Liquid engines provide efficiency, flexibility, and precision at the cost of complexity. Both types remain essential to modern rocketry and are selected based on mission requirements rather than superiority of one over the other. Hybrid rocket engines are a class of rocket engines that use propellants in different physical states, typically a solid fuel and a liquid or gaseous oxidizer. This configuration places hybrid engines between solid and liquid rocket engines in terms of design and operation. They follow the same fundamental principles of rocket propulsion, relying on mass ejection and momentum conservation to generate thrust. In a typical hybrid rocket engine, the fuel is a solid material contained within the combustion chamber, while the oxidizer is stored separately and injected into the chamber during operation. When the oxidizer flows over the surface of the solid fuel, combustion occurs at the fuel surface. The resulting hot gases are expelled through a nozzle to produce thrust. One defining characteristic of hybrid engines is that the fuel and oxidizer are physically separated until combustion occurs. This separation provides inherent safety advantages compared to solid rockets, where fuel and oxidizer are mixed together in a single solid grain. In hybrids, accidental ignition is less likely because combustion cannot occur without the controlled introduction of oxidizer. Thrust control in hybrid rockets is more flexible than in solid engines, but less flexible than in liquid engines. Because the oxidizer flow can be regulated, thrust can be throttled to some extent by increasing or decreasing oxidizer injection. In many designs, shutting off oxidizer flow stops combustion, allowing the engine to be safely shut down, a capability not available in conventional solid rockets. Despite these advantages, hybrid rocket engines face technical challenges. One major limitation is the rate at which the solid fuel surface burns, known as the regression rate. In many hybrid designs, this rate is relatively low, which limits the amount of thrust that can be produced for a given engine size. Increasing thrust often requires larger fuel surfaces or complex internal geometries. Combustion efficiency in hybrid engines can also be lower than in liquid engines. Achieving thorough mixing between the oxidizer and fuel vapor is more difficult when one propellant is solid. Incomplete mixing can reduce performance and make it harder to achieve stable, uniform combustion across the fuel surface. Hybrid engines are mechanically simpler than liquid engines. They do not require high-speed turbopumps to move both fuel and oxidizer. Typically, only the oxidizer must be pumped or pressurized. This reduces system complexity, cost, and the number of failure points compared to fully liquid systems. The choice of fuel and oxidizer in hybrid rockets strongly affects performance. Common solid fuels include synthetic rubbers, plastics, or polymer-based materials, while oxidizers often include liquid oxygen or nitrous oxide. These combinations are chosen for stability, availability, and manageable combustion behavior rather than maximum theoretical efficiency. Hybrid rocket engines have been used primarily in experimental, research, and suborbital applications. Their balance of safety, simplicity, and controllability makes them attractive for educational programs and small-scale launches. However, they are less common in large orbital launch vehicles due to their lower thrust density and scaling challenges. Scaling hybrid engines to very large sizes introduces additional difficulties. Maintaining uniform combustion over large fuel surfaces becomes more complex, and structural considerations increase as chamber size grows. These factors have limited the widespread adoption of hybrids for heavy lift applications. Hybrid engines also face challenges related to fuel grain geometry. As the solid fuel burns, the shape of the internal cavity changes, which affects airflow, combustion behavior, and thrust over time. Designing fuel grains that provide stable, predictable thrust profiles requires careful engineering and testing. In summary, hybrid rocket engines combine features of solid and liquid propulsion systems. They offer improved safety and some degree of thrust control compared to solid rockets, while avoiding much of the mechanical complexity of liquid engines. However, limitations in thrust production, combustion efficiency, and scalability have restricted their use to specialized roles rather than mainstream orbital launch systems. Multi-stage rockets are designed to improve efficiency by discarding parts of the vehicle that are no longer needed during flight. A single rocket stage consists of engines, propellant, tanks, and structural components that operate as a unit. When the propellant in a stage is exhausted, that stage becomes dead weight. Multi-stage rockets solve this problem by separating and dropping spent stages, allowing the remaining vehicle to continue with reduced mass. The fundamental reason for using multiple stages lies in the rocket equation, which shows that the ability to change velocity depends strongly on the ratio between initial mass and final mass. Carrying empty tanks and engines reduces this ratio and wastes energy. By shedding these components once they are no longer useful, A rocket significantly increases its achievable velocity using the same total amount of propellant. In a typical multi-stage rocket, the first stage provides the initial thrust required to lift the vehicle off the ground and overcome the densest part of Earth's atmosphere. This stage usually produces very high thrust and burns for a relatively short time. Once its propellant is depleted, it is separated from the rest of the rocket, often falling back to Earth or, in some designs, being recovered. After first stage separation, the second stage ignites. Because the rocket is now lighter and operating at higher altitude, the second stage can be optimized for efficiency rather than raw thrust. Upper stages usually have smaller engines, longer burn times, and nozzles designed for operation in thinner air or near vacuum. Stage separation is a critical and carefully engineered event. Mechanical systems such as explosive bolts, springs, or pneumatic pushers are used to ensure clean separation. The timing must be precise to avoid collisions or instability. Separation typically occurs when acceleration drops sharply as engines shut down, followed immediately by ignition of the next stage. Multi-stage rockets can have 2, 3, or more stages depending on mission requirements. Two-stage rockets are often sufficient for placing payloads into low Earth orbit, while missions requiring higher velocities, such as geostationary transfer or interplanetary trajectories, commonly use 3 or more stages. Each additional stage increases complexity, but allows greater total velocity. The design of each stage is specialized for its operating environment. Lower stages must withstand high aerodynamic forces, vibration, and heating. Upper stages operate in low-pressure conditions and must manage thermal extremes, long coast phases, and precise engine restarts. As a result, different materials, engines, and structural designs are used for different stages of the same rocket. Staging also allows different propulsion systems to be combined in one vehicle. For example, solid rocket boosters may be used alongside a liquid-fueled core stage to provide extra thrust at liftoff. Once the boosters burn out, they are jettisoned, leaving the liquid engines to continue the ascent. This approach takes advantage of the high thrust of solid rockets and the controllability of liquid engines. There are also performance trade-offs associated with staging. Each stage adds structural mass, separation mechanisms, and potential failure points. Engineers must balance the performance gains from shedding mass against the added weight and complexity of additional stages. Extensive testing and redundancy are required to ensure reliable stage separation and ignition. Some rockets use upper stages that ignite multiple times in space. These stages may perform an initial burn to reach orbit, coast for a period, and then restart to place payloads into specific orbits or trajectories. This capability depends on reliable ignition systems and precise guidance and control. In summary, multi-stage rockets are a direct response to the physical limits imposed by gravity, mass, and energy. By discarding spent stages, rockets avoid carrying unnecessary weight and can achieve the high velocities required for orbital and deep space missions. Staging is not a convenience, but a necessity for efficient spaceflight using chemical propulsion. Rocket structure and materials are critical to performance because every kilogram of mass directly affects how much payload a rocket can deliver. A rocket must be strong enough to survive extreme forces while remaining as light as possible. This requirement drives the use of specialized structural designs and advanced materials that balance strength, stiffness, heat resistance, and low mass. The basic structural shape of most rockets is cylindrical. This geometry efficiently distributes internal pressure from propellant tanks and engine thrust loads while minimizing material usage. Cylindrical and conical shapes also reduce aerodynamic drag during atmospheric flight. Structural sections are often reinforced with internal frames, ribs, or stiffeners to prevent buckling under load. A rocket's structure must withstand several major forces simultaneously. These include thrust forces from the engines, which push upward through the vehicle, aerodynamic forces from air resistance, bending forces caused by wind and steering maneuvers, and vibrational loads generated by engines and airflow. During launch, these forces combine to produce some of the most demanding mechanical environments encountered by any engineered structure. Propellant tanks are a major structural component of many rockets. In liquid-fueled rockets, tanks often make up a large portion of the vehicle's length. These tanks must hold propellants at high or cryogenic pressures while remaining lightweight. To achieve this, tanks are typically made from aluminum alloys, aluminum-lithium alloys, or composite materials designed for high strength-to-weight ratios. Aluminum alloys have been widely used in rocketry because they offer a good balance of strength, low density, corrosion resistance, and manufacturability. Aluminum-lithium alloys further reduce weight while maintaining stiffness, making them common in modern launch vehicles. These materials are carefully treated and welded, using specialized techniques to preserve structural integrity. Composite materials, such as carbon fiber reinforced polymers, are increasingly used in rocket structures. Composites offer very high strength and stiffness at low weight. They are commonly used in payload fairings, interstage structures, and some propellant tanks. However, composites can be sensitive to impact damage and thermal extremes, requiring careful design and inspection. Rocket engines and areas near the exhaust experience extreme temperatures. Combustion chambers and nozzles are exposed to heat that can exceed several thousand degrees Celsius. To survive these conditions, high-temperature materials such as nickel-based superalloys, copper alloys, and specialized steels are used. These materials retain strength at high temperatures and resist deformation and cracking. Thermal protection is essential in many parts of a rocket. Some components use ablative materials that slowly erode, carrying heat away from the structure. Others rely on insulation or active cooling systems. In liquid engines, cryogenic propellants are often circulated through channels around the combustion chamber and nozzle to absorb heat before being burned, reducing thermal stress on engine walls. Fasteners, joints, and welds are critical points in rocket structures. These areas experience concentrated stresses and must be carefully engineered to avoid failure. Welding techniques such as friction stir welding are commonly used to create strong, defect-resistant joints in aluminum structures. In composite structures, bonding and layering techniques are precisely controlled to ensure reliability. Vibration and acoustic loads during launch can be severe. Rocket engines generate intense sound waves that can shake the vehicle and its payload. Structural components are designed to damp or withstand these vibrations without resonating at damaging frequencies. Payloads are often isolated using shock-absorbing mounts to protect sensitive instruments. Mass optimization is a constant focus in rocket structural design. Engineers analyze every component to remove unnecessary material while maintaining safety margins. This process involves extensive computer modeling, ground testing, and flight data analysis. Even small mass savings can significantly improve payload capacity or mission flexibility. In summary, rocket structures are engineered to survive extreme mechanical and thermal environments while remaining as light as possible. The choice of materials and structural design reflects a balance between strength, durability, manufacturability, and mass efficiency. Advances in materials science and structural engineering continue to play a central role in improving rocket performance and reliability. Atmospheric flight is one of the most demanding phases of a rocket's journey because the vehicle must operate simultaneously as a high-speed aerospace object and a space launch system. During this phase, the rocket travels through layers of air that vary rapidly in density, temperature, and pressure, while accelerating to extreme speeds. The interaction between the rocket and the atmosphere creates forces and stresses that strongly influence vehicle design and flight profile. As a rocket ascends, It passes through the troposphere, stratosphere, mesosphere, and lower thermosphere. Air density decreases exponentially with altitude. Near the ground, the air is dense and produces strong aerodynamic forces. At higher altitudes, the air becomes thin, reducing drag and aerodynamic loading. Rocket guidance systems are designed to account for these changing conditions continuously. One of the primary atmospheric forces acting on a rocket is aerodynamic drag. Drag opposes the rocket's motion and increases with both air density and the square of velocity. During ascent, rockets pass through a region where velocity is increasing rapidly, while air density is still significant. This creates a peak drag condition that strongly affects structural design and trajectory planning. The point of maximum aerodynamic stress is known as maximum dynamic pressure. Often called max Q, dynamic pressure is a measure of the force exerted by airflow on the vehicle. At max Q, the combined effects of speed and air density produce the highest aerodynamic loads experienced during flight. Rockets are often throttled down slightly near this point to reduce stress on the structure. Aerodynamic heating is another major effect of atmospheric flight. As a rocket moves through air at high speed, friction and compression of air at the vehicle's surface generate heat. Although rockets do not experience the same extreme heating as spacecraft during re-entry, heating during ascent is still significant, especially around leading edges, engine nozzles, and protruding structures. The shape of the rocket is optimized to manage aerodynamic forces. Most rockets have smooth, slender bodies to reduce drag and avoid flow separation. Payload fairings are designed to protect cargo from aerodynamic loads and heating, while maintaining an efficient shape. Any irregularities in shape can create turbulence, increasing drag and vibration. Aerodynamic stability is critical during atmospheric flight. A rocket must remain pointed in the correct direction despite wind, turbulence, and thrust variations. Stability is achieved through a combination of vehicle shape, mass distribution, and active control systems. Early rockets used fins for stabilization, but modern launch vehicles rely primarily on guidance systems and engine gimbaling. Winds can significantly affect rocket flight in the atmosphere. Wind speed and direction vary with altitude, creating shear forces that can bend the rocket. Launch conditions are carefully monitored, and launches are delayed if winds exceed safe limits. Guidance systems continuously adjust thrust direction to compensate for wind-induced deviations. Acoustic forces are particularly intense during atmospheric flight. Rocket engines produce powerful sound waves that interact with the surrounding air and reflect off the vehicle and launch structures. These acoustic loads can induce vibrations throughout the rocket and payload. Structural damping and insulation are used to protect sensitive components. As the rocket climbs, atmospheric effects diminish rapidly. Drag decreases, aerodynamic heating lessens, and control authority gradually shifts from aerodynamic considerations to purely inertial motion. Control systems transition from managing airflow-related forces to operating in near-vacuum conditions, where only thrust and gravity matter. The timing of stage separation is influenced by atmospheric conditions. Lower stages are usually designed to operate within the atmosphere and are separated once their role in overcoming drag and gravity is complete. Upper stages ignite at higher altitudes where air resistance is minimal, allowing engines and nozzles optimized for vacuum operation to perform efficiently. In summary, atmospheric flight is a complex and critical phase of rocket ascent. The rocket must withstand drag, heating, vibration, wind, and changing pressure while accelerating rapidly. These challenges arise from fundamental fluid dynamics and atmospheric physics, making atmospheric flight one of the key drivers of rocket design, guidance, and operational limits alone, but by achieving a specific state of motion around Earth. An object is in orbit when it is moving forward fast enough that, as it falls toward Earth under gravity, the surface of the planet curves away beneath it at the same rate. The object is therefore in continuous free fall, constantly accelerating downward due to gravity, while simultaneously moving sideways at very high speed. If the sideways velocity is insufficient, the trajectory intersects Earth, and the object re-enters the atmosphere. For low Earth orbit, the required horizontal velocity is approximately 7.8 kilometers per second, or about 28,000 kilometers per hour. This value varies slightly with altitude and Earth's rotation, but remains within a narrow range. The key requirement is velocity parallel to Earth's surface, not vertical height. A rocket can reach altitudes higher than many satellites without achieving orbit if it does not accelerate sideways to the necessary speed. Conversely, an object at relatively modest altitude can remain in orbit if its horizontal velocity is sufficient. During launch, rockets do not travel straight upward for the entire ascent. They initially rise vertically to clear dense atmospheric layers and avoid excessive aerodynamic stress. As altitude increases and air density decreases, the rocket gradually tilts, redirecting thrust from vertical lift to horizontal acceleration. This controlled rotation of the flight path is known as a gravity turn. It allows gravity to naturally bend the trajectory, reducing steering losses and improving fuel efficiency. Orbit is sometimes incorrectly described as a balance between gravity and an outward force. In reality, gravity is never canceled. Gravity provides the centripetal acceleration that continually bends the spacecraft's path around Earth. The sensation of weightlessness experienced by astronauts occurs because both the spacecraft and everything inside it are falling together under gravity, not because gravity is absent. At typical orbital altitudes, Earth's gravitational pull remains close to its surface value. The relationship between orbital altitude and velocity is counterintuitive. Lower orbits require higher speeds, while higher orbits require lower speeds. This occurs because gravity is stronger closer to Earth, requiring faster motion to maintain a curved path that does not intersect the planet. As altitude increases and gravitational acceleration weakens, the required orbital speed decreases. This principle governs the structure of all Earth orbits, from very low Earth orbit to geostationary orbit. Earth's rotation provides a measurable advantage for launches. At the equator, Earth's surface moves eastward at roughly 465 meters per second due to rotation. Launching eastward allows rockets to add this velocity to their own, reducing the propellant required to reach orbit. This is why many launch sites are located at low latitudes, and why most orbital launches head east over oceans to minimize risk to populated areas. Reaching orbit is a process rather than a single moment. Rockets typically reach orbital altitude before reaching orbital speed, after the atmosphere has thinned to near vacuum. Upper stages continue firing for several minutes to build horizontal velocity. Only when the spacecraft's trajectory closes around Earth, forming a stable path rather than a ballistic arc, is orbit achieved. Mission controllers confirm orbit by tracking the spacecraft over multiple revolutions. The final engine burn that establishes a stable orbit is called orbital insertion. If this burn is too short, the spacecraft enters a suborbital trajectory and re-enters the atmosphere. If the burn is too long, the spacecraft may enter a higher-than-planned orbit or exceed Earth's escape velocity. Orbital insertion therefore requires precise timing, accurate navigation, and tightly controlled engine performance. Even after orbit is achieved, atmospheric drag remains relevant at low altitudes. Trace amounts of atmosphere extend hundreds of kilometers above Earth's surface. This residual drag gradually removes energy from low-orbiting spacecraft, causing their orbits to decay over time. Without periodic propulsion maneuvers, satellites in low Earth orbit will eventually descend and re-enter the atmosphere. This is a fundamental limitation of low orbits, not a design flaw. From an energy perspective, reaching orbit is the most demanding part of spaceflight. The majority of a rocket's propellant is consumed simply to achieve orbital velocity. Once in orbit, traveling to much more distant destinations requires comparatively smaller increases in energy. Historical missions such as Apollo 11 demonstrated this clearly. Most of the Saturn V's energy was spent reaching Earth orbit before the journey to the Moon even began. Modern launch systems, including vehicles such as Falcon Heavy, obey the same physical requirements as early rockets. Advances in materials, computing, and propulsion have improved efficiency and reliability, but the fundamental physics of orbit have not changed. Reaching orbit is ultimately about achieving the correct speed and direction, not escaping gravity, and this principle applies to all orbital spacecraft without exception. Payloads are the primary reason rockets are launched. A payload is any object carried by a rocket that is intended to perform a function once the rocket has completed its job. Payloads can include satellites, scientific instruments, crewed spacecraft, cargo modules, planetary probes, and technology demonstrations. The rocket itself is a delivery system. The payload is the mission. Payload mass is one of the most critical factors in rocket design. The heavier the payload, the more thrust and propellant are required to reach orbit. This relationship is not linear. Adding payload mass increases the required fuel, which in turn increases the total mass of the rocket, requiring even more fuel. This compounding effect strongly limits how much mass can be delivered to space and drives the need for lightweight materials and efficient propulsion. Satellites are the most common type of payload. They serve functions such as communication, navigation, weather monitoring, Earth observation, and scientific research. Satellite payloads include not only the satellite structure itself, but also antennas, sensors, power systems, fuel, and onboard computers. Every component must survive launch forces and operate reliably in vacuum, radiation, and extreme temperature variations. Crewed payloads include spacecraft designed to carry humans. These payloads require life support systems, pressure vessels, thermal control, radiation shielding, and emergency systems. Human-rated payloads are significantly heavier and more complex than uncrewed satellites due to safety requirements. Crew capsules and space station modules are examples of payloads designed around human survival rather than minimal mass. Cargo payloads transport supplies such as food, water, fuel, tools, experiments, and replacement hardware. These payloads support long-duration missions and orbital facilities like the International Space Station. Cargo mass directly affects mission planning because heavier resupply launches require more powerful rockets or reduced payload volume. Scientific payloads are often optimized for precision rather than durability. Space telescopes, particle detectors, and planetary instruments are designed to collect data with minimal interference. These payloads may include mirrors, spectrometers, cameras, and sensors that must remain precisely aligned. Launch vibration and acoustic forces place strict constraints on how scientific payloads are mounted and protected. Payload volume is as important as payload mass. Rockets enclose payloads inside a payload fairing, which protects them during atmospheric flight. The fairing size limits the physical dimensions of the payload. Large but lightweight payloads may be constrained by volume, even if their mass is within limits. Fairing shape and diameter are therefore critical design parameters for launch vehicles. Payload integration is the process of mounting the payload onto the rocket. This includes mechanical attachment, electrical connections, and software interfaces. Payloads must be securely fastened to withstand acceleration forces that can exceed several times Earth's gravity. At the same time, separation systems must reliably release the payload once orbit is reached without imparting damaging forces. The payload's destination determines the energy required for launch. Reaching low Earth orbit requires less energy than reaching geostationary orbit or sending a probe to another planet. Payloads destined for higher orbits reduce the allowable mass for a given rocket. Mission planners must trade payload mass against orbital altitude and inclination. Some payloads are designed to separate into multiple components after launch. Rideshare missions carry several smaller satellites on a single rocket, reducing launch costs. Each payload must deploy without interfering with others. This requires precise timing and sequencing of separation events to avoid collisions. Payloads may include propulsion systems of their own. Many satellites carry onboard thrusters to raise or adjust their orbits after deployment. This allows the launch vehicle to place the payload into a temporary or transfer orbit, reducing the rocket's workload. The inclusion of onboard propulsion increases payload mass, but improves mission flexibility. Thermal considerations are critical for payloads. During launch, payloads experience heating from aerodynamic friction. In orbit, they are exposed to alternating sunlight and darkness, causing large temperature swings. Payload thermal control systems use insulation, radiators, and heaters to maintain operating temperatures. Radiation exposure is another constraint. Outside Earth's atmosphere, payloads are exposed to cosmic rays and charged particles from the sun. Electronics must be shielded or hardened to prevent damage and data corruption. This is especially important for long-duration missions and sensitive scientific instruments, such as those carried by the Hubble Space Telescope. Payload performance ultimately defines mission success. A rocket launch is considered successful only if the payload reaches its intended orbit and becomes operational. From a mission perspective, the rocket is a temporary system, while the payload is the enduring asset. Rocket engineering is therefore driven not by the vehicle itself, but by the demands, limitations, and objectives of the payload it carries. Rockets are subjected to extreme heat, vibration, and mechanical stress throughout their operation, especially during launch and ascent. These conditions arise from high engine thrust, rapid acceleration, atmospheric drag, and structural loading. Designing a rocket requires accounting for all these stresses simultaneously, because failure in any one area can compromise the entire vehicle. Thermal stress begins at ignition. Rocket engines operate at extremely high combustion temperatures, often exceeding 3,000 degrees Celsius inside the combustion chamber. Engine components must withstand these temperatures without melting, deforming, or failing. This is achieved through a combination of high-temperature alloys, ceramics, and active cooling methods such as regenerative cooling, where cryogenic propellant is circulated through engine walls to absorb heat before combustion. As the rocket ascends through the atmosphere, aerodynamic heating becomes significant. Friction between the vehicle and surrounding air causes surface temperatures to rise, particularly at leading edges and exposed structures. Although this heating is far less intense than atmospheric reentry heating, it still imposes strict limits on materials, coatings, and structural design. The heating profile changes rapidly with altitude as air density decreases. Mechanical stress is highest during the first minutes of flight. Rocket structures must support their own weight while accelerating upward under thrust forces that can exceed several times Earth's gravity. Tanks, interstage connections, and engine mounts experience compressive, tensile, and shear loads simultaneously. These loads vary dynamically as propellant mass decreases and thrust levels change. One of the most challenging environments occurs at maximum aerodynamic pressure, commonly referred to as max Q. This is the point during ascent when the combination of high velocity and relatively dense atmosphere produces the greatest aerodynamic force on the vehicle. At max Q, even small structural weaknesses can lead to buckling or failure. Launch profiles are carefully designed to throttle engines or adjust trajectory to limit stress during this phase. Vibration is generated primarily by rocket engines. Combustion instability, turbopump operation, and exhaust flow all produce oscillations that propagate through the vehicle. These vibrations can range from low-frequency structural modes to high-frequency acoustic vibrations. Payloads and onboard systems must be designed to tolerate this environment without mechanical damage or loss of functionality. Acoustic stress is a major concern at liftoff. Rocket engines produce extremely intense sound waves, with sound pressure levels that can exceed 180 decibels near the launch pad. These acoustic waves can reflect off surfaces and couple with the rocket structure, inducing vibrations capable of damaging sensitive components. Launch pads use flame trenches, water deluge systems, and sound suppression techniques to reduce acoustic energy. Thermal gradients also create stress. Different parts of a rocket heat and cool at different rates, causing materials to expand or contract unevenly. This can lead to internal stress even when overall temperatures are within safe limits. Engineers must carefully select materials with compatible thermal expansion properties and design joints that can tolerate movement without cracking. Cryogenic propellants introduce additional challenges. Liquid oxygen and liquid hydrogen are stored at extremely low temperatures. When tanks filled with cryogenic fluids are exposed to warm external conditions, large temperature differences develop across tank walls. These conditions can cause material embrittlement, thermal contraction, and increased stress concentrations if not properly managed. Payloads experience many of the same stresses as the rocket itself. Satellites and crewed spacecraft must survive launch acceleration, vibration, and acoustic loads. For this reason, payloads undergo extensive ground testing, including vibration tables, acoustic chambers, and thermal vacuum tests, to verify their ability to withstand launch conditions without degradation. Structural margins are deliberately conservative. Rockets are designed with safety factors that allow them to tolerate stresses beyond expected operational limits. This approach accounts for uncertainties in material properties, manufacturing variations, and environmental conditions. However, increasing structural margin also increases mass, which reduces payload capacity, creating a constant trade-off in design. Historical launch failures have demonstrated the consequences of inadequate stress management. Structural collapse, engine failure due to thermal overload, and vibration-induced component damage have all led to mission losses. These failures have driven advances in modeling, testing, and materials science, improving reliability across the launch industry. Modern rockets rely heavily on computational simulations to predict heat flow, vibration modes, and stress distribution. These simulations are validated through testing and flight data. Despite advances in analysis tools, real-world conditions remain complex, and rockets are still among the most mechanically stressed machines ever built. Heat, vibration, and mechanical stress are not secondary concerns in rocketry. They are central design drivers. Every component, from engines to avionics to payload mounts, must function reliably in an environment that pushes materials and structures close to their limits. Successful launches demonstrate precise control over these extreme physical conditions rather than their elimination. Reusable rockets are launch vehicles designed to recover and fly major components more than once, instead of discarding them after a single flight. Historically, most rockets were expendable, meaning stages were destroyed or left in the ocean or space after use. Reusability aims to reduce launch costs, shorten turnaround time, and improve launch frequency by spreading manufacturing and development costs across multiple missions. The primary technical challenge of reusability is surviving return from space or near-space conditions. Rocket stages experience extreme heating, structural loads, and dynamic forces during ascent. To be reusable, they must also endure additional stress during descent, re-entry, and landing. This requires stronger structures, thermal protection, guidance systems, and landing hardware, all of which add mass and complexity. The most common reusable approach involves recovering the first stage of an orbital rocket, the first stage provides the majority of thrust during liftoff and is the largest and most expensive portion of the vehicle. After stage separation, the first stage performs controlled maneuvers to return to Earth. These maneuvers include a boost back burn to reverse horizontal motion, a re-entry burn to reduce heating, and a landing burn to achieve a controlled touchdown. Guidance and navigation are critical to successful recovery. Reusable stages rely on inertial sensors, GPS, onboard computers, and engine throttling to precisely control descent. Small errors in timing or thrust can result in structural overload or impact failure. Landing accuracy must be within meters, especially when landing on floating platforms at sea. Thermal stress during re-entry is a major design constraint. Unlike spacecraft designed for orbital re-entry, reusable rocket stages re-enter the atmosphere at lower speeds, but with less protective shielding. Heat loads must be carefully managed using engine burns to reduce velocity, and by designing structures that can tolerate elevated temperatures without ablative heat shields. Landing systems vary by design. Some reusable rockets land vertically using their main engines, while others may be recovered by parachutes or other aerodynamic methods. Vertical landing requires deep engine throttling capability, rapid engine restart, and stable control during the final seconds of descent. The landing structure must absorb residual forces without damaging critical systems. Reusability affects payload capacity. Because reusable stages must carry additional fuel for return maneuvers and extra structural mass for landing systems, they typically deliver less payload to orbit compared to fully expendable configurations. Launch operators must choose between maximum payload and stage recovery based on mission requirements and economics. Turnaround time is another key factor. Recovering a stage does not automatically make launches cheaper if refurbishment is slow or costly. Reusable rockets must be inspected, tested, and refurbished efficiently. Components such as engines, tanks, valves, and avionics are examined for wear, thermal damage, and fatigue before reuse. The goal is to minimize refurbishment while maintaining safety and reliability. The economic benefit of reusability depends on flight rate. High launch frequency allows recovered hardware to be reused often, reducing the cost per flight. At low flight rates, the savings from reuse may not offset the additional development and operational complexity. Reusability, therefore, favors operators with consistent demand and standardized vehicle designs. The most prominent operational example of orbital-class reusability is the first stage recovery system used by SpaceX on its Falcon series launch vehicles. Recovered stages have flown multiple times, demonstrating that rocket hardware can survive repeated launches with controlled maintenance. This has changed industry assumptions about launch cost structures and vehicle lifespan. Reusable concepts have existed for decades. The space shuttle used reusable components but required extensive refurbishment between flights, limiting cost savings. Modern reusable rockets focus on partial reuse with simpler systems, trading full reusability for operational efficiency and reliability. Reusability also introduces new operational risks. Landing failures can destroy stages even after a successful launch. Weather, sea conditions, and hardware anomalies all affect recovery success. As a result, reuse strategies must balance risk tolerance against cost reduction goals. From an engineering perspective, reusable rockets represent a shift in design philosophy. Instead of optimizing solely for one-time performance, engineers must consider durability, fatigue life, and repeated thermal cycling. Material selection, structural margins, and engine design are influenced by the need to survive multiple missions. Reusable rockets have not changed the fundamental physics of spaceflight. Orbital velocity requirements, propellant mass fractions, and energy constraints remain the same. What has changed is the economic model of access to space. Reusability reduces waste, shortens manufacturing cycles, and enables higher launch cadence, making space operations more sustainable and flexible over time. Rocket failures and anomalies are events in which a launch vehicle does not perform as intended, resulting in partial or total mission loss. These outcomes range from catastrophic explosions to subtle performance deviations that prevent a payload from reaching its planned orbit. Failures are inherent risks in rocketry due to the extreme energies, tight tolerances, and complex interactions involved in launch operations. Failures are commonly categorized by when they occur. Pad failures happen before liftoff, often during fueling or engine ignition, and are usually caused by leaks, valve malfunctions, or ignition instability. Ascent failures occur after liftoff and may result from structural collapse, engine shutdown, guidance errors, or aerodynamic overload. Upper stage failures typically occur later in flight and can prevent orbital insertion even if the early phases of launch were successful. Engine-related issues are among the most frequent causes of failure. Rocket engines operate under extreme pressure and temperature, and small defects can lead to combustion instability, turbopump failure, or loss of thrust. An engine that shuts down early or produces uneven thrust can destabilize the vehicle or reduce velocity below orbital requirements. Redundancy and engine-out capability are used in some designs to mitigate this risk. Structural failures occur when loads exceed design limits or when materials behave unexpectedly. These failures may involve tank rupture, interstage collapse, or attachment point failure. Structural problems often emerge during periods of peak stress, such as maximum aerodynamic pressure or rapid acceleration late in first-stage flight. Even minor manufacturing defects or unexpected material behavior can propagate into catastrophic outcomes. Guidance, navigation, and control anomalies can also cause mission loss. Rockets rely on sensors, computers, and software to maintain correct orientation and trajectory. Faulty sensor data, software errors, or actuator malfunctions can lead to loss of control. In some cases, rockets are intentionally destroyed by range safety systems when they deviate from safe flight corridors to protect people and infrastructure on the ground. Propellant system failures include leaks, incorrect mixture ratios, and pressurization problems. Cryogenic propellants introduce additional complexity due to extreme temperatures and rapid phase changes. Improper tank pressurization can cause structural collapse or engine starvation. These failures may develop gradually or occur suddenly with little warning. Upper stage anomalies are particularly challenging because they often occur after most systems have performed successfully. Failures at this stage may involve ignition failure, premature engine cutoff, or loss of attitude control. Because upper stages operate in near vacuum conditions, diagnosing problems can be difficult, and recovery options are limited once a burn fails. Payload separation failures are another significant category. Even if a rocket reaches orbit, the mission can fail if the payload does not separate correctly. Separation mechanisms must function reliably after enduring launch stresses and thermal cycling. Failure to deploy can render a satellite unusable despite an otherwise successful launch. Historical failures have played a major role in improving rocket reliability. Investigations conducted by organizations such as NASA have identified root causes ranging from design flaws to management and communication failures. Lessons learned from these investigations have led to changes in engineering standards, testing procedures, and organizational practices across the aerospace industry. Statistical reliability has improved significantly over time. Early orbital rockets had failure rates exceeding 20%. Modern launch vehicles typically achieve success rates above 95%, depending on vehicle maturity and operational history. This improvement is the result of incremental advances rather than single breakthroughs, including better materials, more accurate modeling, and extensive ground testing. Testing is central to failure reduction. Components undergo static firing, vibration testing, thermal cycling, and pressure testing to uncover weaknesses before flight. Flight data from both successful and failed missions is used to refine models and update design margins. Modern rockets are heavily instrumented, allowing engineers to analyze thousands of data points to understand anomalies in detail. Commercial launch providers such as SpaceX and Arianespace publicly document failures and corrective actions as part of regulatory and customer requirements. Transparency in failure analysis helps prevent recurrence and contributes to industry-wide safety improvements. Despite advances, rocket failures cannot be eliminated entirely. Space launch remains a high-risk activity constrained by physics and engineering limits. Each mission involves controlled exposure to extreme conditions, and residual risk is unavoidable. Reliability improvements therefore focus on reducing failure probability, improving fault tolerance, and ensuring that when failures occur, they are understood and used to strengthen future systems. Rockets and missiles share a common technological foundation, but differ fundamentally in purpose, operational context, and design priorities. Both are self-propelled vehicles that use rocket engines to generate thrust by expelling mass at high velocity. The underlying physics, including Newton's laws of motion, propulsion principles, and basic guidance concepts, apply equally to both systems. However, their missions diverge sharply, shaping how they are engineered and used. Rockets are primarily designed for space access and scientific, commercial, or exploratory missions. Their objective is to deliver payloads such as satellites, crewed spacecraft, probes, or cargo to specific orbits or trajectories beyond Earth's surface. Missiles, by contrast, are weapon systems designed to deliver destructive payload to terrestrial or maritime targets. Accuracy, response time, and reliability under combat conditions dominate missile design priorities. Trajectory profiles represent a major difference. Space launch rockets typically follow carefully optimized ascent paths that maximize payload efficiency while minimizing structural and aerodynamic stress. These trajectories involve gradual pitch-over maneuvers and precise orbital insertion burns. Missiles, especially ballistic missiles, are optimized for rapid delivery and may follow steep, high-arc trajectories designed to maximize range, minimize interception time, or exploit specific flight characteristics. Payload characteristics also differ significantly. Rocket payloads are usually non-destructive and must remain functional after deployment. They may operate for years or decades and require protection from launch vibration, radiation, and thermal extremes. Missile payloads are designed to deliver kinetic or explosive effects upon impact or detonation, and are not required to remain operational after delivery. This distinction strongly influences structural design, separation mechanisms, and onboard systems. Guidance and control systems reflect mission differences. Space rockets use guidance systems optimized for precise orbital parameters, including velocity, inclination, and altitude. Small errors can result in mission failure even if the vehicle remains intact. Missiles emphasize target accuracy and robustness against countermeasures. Some missiles rely on inertial guidance alone, while others incorporate radar, satellite navigation, or terminal guidance systems to adjust course near the target. Range and velocity requirements overlap, but are not identical. Orbital rockets must reach extremely high horizontal velocities to remain in orbit, often exceeding those required by most missiles. Intercontinental ballistic missiles approach orbital speeds, but typically follow suborbital trajectories that intersect Earth rather than circling it. The difference lies not in maximum speed alone, but in whether sustained orbital motion is intended. Reusability is another point of divergence. Modern space rockets increasingly incorporate reusable components to reduce cost and increase launch cadence. Missiles are almost always expendable by design, as they are intended for one-time use in military contexts. Durability for repeated flights is therefore not a design goal for missile systems. Operational environments also differ. Space launches are conducted from fixed sites with extensive infrastructure, long preparation times, and strict safety controls. Missile launches must be possible from a variety of platforms, including mobile ground vehicles, submarines, aircraft, and ships. This requirement drives compact design, rapid readiness, and environmental resilience in missile systems. Legal and regulatory frameworks clearly separate rockets and missiles. Space launch vehicles operate under civilian and international space law, including treaties governing peaceful use of outer space. Missile systems are regulated under military doctrine and arms control agreements. Although the technology overlaps, the intent and legal classification determine how systems are developed, tested, and deployed. Historically, early rocket development blurred the distinction between the two. Many early space launch technologies evolved from military missile programs during the mid-20th century. Over time, the divergence in mission requirements led to specialized designs optimized either for space access or for weapon delivery. Today, although some components and engineering methods remain similar, rockets and missiles are rarely interchangeable without major modification. Organizations such as NASA focus exclusively on civilian spaceflight and scientific missions, while missile development is typically handled by defense agencies and contractors under military authority. This institutional separation reinforces the functional and ethical differences between the two systems. In summary, rockets and missiles are based on the same physical principles, but are defined by their objectives. Rockets are transportation systems designed to place payloads into space or onto interplanetary trajectories. Missiles are weapons designed to deliver payloads to targets on Earth. The differences in purpose drive differences in design, operation, regulation, and long-term impact, making the distinction between the two both practical and fundamental. Rocket launches produce extreme levels of sound and light as direct consequences of high-energy combustion and rapid gas expansion. These effects are not incidental. They are unavoidable physical results of converting chemical energy into thrust at very high power levels. The intensity of sound and brightness scales with engine size, thrust, exhaust velocity, and operating pressure. Sound from a rocket originates primarily in the exhaust plume. Inside the engine, propellants burn at very high pressure and temperature, producing hot gases that are expelled through a nozzle at supersonic speed. When this exhaust exits the nozzle and interacts with the surrounding air, it generates powerful pressure waves. These pressure fluctuations propagate outward as sound. The greater the mass flow rate and exhaust velocity, the higher the acoustic power produced. Sound pressure levels near the launch pad routinely exceed 170 to 180 decibels, making rocket launches among the loudest human-made events. At these levels, sound waves carry enough energy to damage structures, rupture components, and cause physical harm. The sound intensity decreases rapidly with distance, but it can still be heard and felt many kilometers away due to the enormous initial energy. Acoustic energy is particularly dangerous because it couples with structures. Sound waves can induce vibrations in rocket bodies, payloads, and launch infrastructure. These vibrations can excite structural resonances, potentially leading to fatigue or failure. For this reason, acoustic loads are treated as a primary design constraint for both launch vehicles and payloads. Launch facilities employ sound suppression systems to mitigate acoustic effects. The most common method is a water deluge system that releases large volumes of water onto the launch pad and into flame trenches at ignition. Water absorbs and scatters sound energy, reducing reflected acoustic waves. This does not silence the rocket, but significantly lowers the intensity of sound that reflects back toward the vehicle. flame trenches and exhaust deflectors also play a role. By directing exhaust away from the rocket and pad, they reduce the amount of sound energy that reflects upward. Without these structures, reflected pressure waves could severely damage the vehicle during liftoff. The geometry of launch pads is therefore carefully engineered to manage acoustic flow. The brightness of a rocket launch comes primarily from the exhaust plume. Combustion produces extremely hot gases that emit light across a wide range of wavelengths. The exact color and intensity depend on propellant chemistry, combustion temperature, and exhaust composition. Hydrogen-oxygen engines tend to produce relatively faint, pale exhaust in daylight, but extremely bright plumes at night, while kerosene-based engines produce bright orange flames due to glowing carbon particles. At night, rocket plumes can appear dramatically larger and brighter than during the day. This is partly due to human visual perception and partly due to interaction with the upper atmosphere. Exhaust gases expanding into thin air can fluoresce or scatter sunlight long after sunset, creating large glowing clouds visible over wide areas. Light is also produced by shock structures in the exhaust. As supersonic exhaust expands and recompresses, shock diamonds form within the plume. These regions are associated with localized increases in temperature and pressure, contributing to visible patterns and fluctuations in brightness. These structures are direct indicators of exhaust dynamics and nozzle performance. The intensity of light from a launch is sufficient to illuminate clouds, terrain, and surrounding structures over large distances. In some cases, rocket launches have been mistaken for natural phenomena because of their brightness and unusual visual appearance. This effect is strongest for high-altitude exhaust interacting with sunlight at low angles. Sound and light are closely linked during launch, but behave differently as distance increases. Sound attenuates relatively quickly with distance and atmospheric conditions, while light can remain visible over hundreds of kilometers under the right conditions. As a result, observers far from a launch site may see a bright plume without hearing the launch. From an engineering perspective, managing sound and light is not about elimination but control. Acoustic loads must be reduced to levels that structures and payloads can survive. Light intensity is generally not harmful, but provides valuable diagnostic information. High-speed cameras and optical sensors analyze plume brightness, shape, and color to assess engine health during flight. Sound and light from rockets are therefore not byproducts, but signatures of extreme energy transfer. They reflect the fundamental reality of rocket propulsion. Large amounts of mass are accelerated to very high speeds in a short time. The resulting acoustic and optical effects are among the most visible and measurable indicators of the forces involved in reaching space. Rocket launches have measurable environmental effects that occur locally at launch sites and globally at higher altitudes. These effects arise from propellant combustion, exhaust byproducts, acoustic energy, debris generation, and long-term accumulation of objects in orbit. While the total number of launches is small compared to other industrial activities, the unique operating environment of rockets means their impacts are concentrated and scientifically distinct. Exhaust emissions are the primary direct environmental output of rocket launches. Chemical rockets expel large quantities of gases at high temperature, including water vapor, carbon dioxide, nitrogen oxides, carbon monoxide, and unburned hydrocarbons. Depending on propellant type, solid rocket motors additionally emit aluminum oxide particles and hydrogen chloride gas. The composition of exhaust varies widely between propulsion systems, making environmental impact strongly dependent on rocket design. Water vapor is the dominant exhaust product for hydrogen-oxygen engines. When released into the upper atmosphere, water vapor can persist longer than at ground level and influence local atmospheric chemistry. At high altitudes, water vapor can contribute to cloud formation and affect radiative balance. Although the overall global contribution from rocket launches remains small compared to natural sources. Carbon dioxide emissions from rocket launches are relatively low on a global scale when compared to aviation, shipping, or power generation. However, rockets release emissions directly into the upper troposphere, stratosphere, and mesosphere, where atmospheric mixing is slower. This makes the location of emissions more relevant than their total quantity when assessing environmental impact. Solid rocket exhaust introduces additional concerns. Hydrogen chloride gas released during combustion can temporarily increase local acidity in rainfall near launch sites. Aluminum oxide particles can remain suspended in the upper atmosphere and act as condensation nuclei, potentially influencing ozone chemistry. These effects are localized and short-lived near launch facilities, but are an important consideration in environmental assessments. Acoustic energy and heat released at launch sites affect local ecosystems. The intense sound pressure generated during liftoff can disturb wildlife, particularly birds and marine animals near coastal launch facilities. Heat and exhaust can damage vegetation close to the pad. For this reason, launch sites are typically located in remote or controlled areas, and environmental monitoring is conducted before and after launches. Launch debris is another environmental factor. Ice, insulation foam, and small fragments can fall into surrounding land or ocean areas during ascent. Launch providers establish debris zones and recovery plans to minimize risk to people and ecosystems. Modern launch operations carefully model debris dispersion to limit environmental impact. In orbit, environmental concerns shift from emissions to debris accumulation. Spent rocket stages, defunct satellites, and fragments from collisions contribute to orbital debris. This debris poses a collision risk to operational spacecraft and can generate further debris through cascading impacts. Although not an atmospheric effect, orbital debris is an environmental issue specific to the near-Earth space environment. Mitigation measures are increasingly incorporated into rocket operations. Launch providers design upper stages to deorbit after mission completion, reducing long-term debris accumulation. Some rockets reserve propellant specifically for controlled re-entry to ensure hardware burns up safely in the atmosphere, rather than remaining in orbit indefinitely. Reusable rockets influence environmental impact in multiple ways. Reusability reduces the need to manufacture entire vehicles for each launch, lowering material consumption and industrial waste. However, reusable stages may release additional exhaust during landing burns. The net environmental effect depends on launch frequency, refurbishment processes, and operational efficiency. Environmental regulation plays a central role in launch approval. Space agencies and launch operators work with regulatory bodies to assess environmental impact through formal studies. Organizations such as NASA and European Space Agency conduct environmental reviews to evaluate emissions, noise, debris, and ecological effects associated with launch activities. Future launch systems aim to reduce environmental impact further. Research focuses on cleaner propellants, improved combustion efficiency, reduced particulate emissions, and operational practices that limit debris. Some experimental engines explore non-toxic propellants for upper stages and spacecraft maneuvering systems to reduce environmental hazards. In summary, the environmental effects of rockets are real but highly specialized. They differ from conventional pollution due to altitude, intensity, and frequency. While rockets contribute a small fraction of global emissions, their impacts occur in sensitive atmospheric layers and orbital regions. Managing these effects requires careful engineering, regulation, and ongoing scientific study as launch activity continues to increase. Rockets remain essential because they are currently the only proven technology capable of transporting significant payloads from Earth's surface into space. No alternative system has demonstrated the ability to reliably overcome Earth's gravity, operate independently of the atmosphere, and deliver payloads to precise orbits or interplanetary trajectories. Despite advances in other areas of aerospace technology, rockets remain indispensable for access to space. Modern society relies heavily on space-based infrastructure enabled by rockets. Communication satellites support global telecommunications, internet connectivity, television broadcasting, and emergency services. Navigation systems provide precise positioning and timing used in aviation, shipping, agriculture, financial networks, and everyday consumer devices. Without rockets, maintaining and expanding these satellite networks would be impossible. Rockets are critical for Earth observation and environmental monitoring. Satellites launched by rockets track weather patterns, monitor climate change, observe deforestation, measure sea level rise, and detect natural disasters. These observations provide data that cannot be collected effectively from the ground and play a key role in forecasting, disaster response, and long-term environmental planning. Scientific research depends on rockets to place instruments above Earth's atmosphere. Space telescopes avoid atmospheric distortion and absorption, enabling observations across a wide range of wavelengths. Scientific satellites study Earth's magnetic field, solar activity, cosmic radiation, and fundamental physics phenomena. Rockets make it possible to conduct experiments in microgravity, revealing physical and biological processes that cannot be isolated on Earth. Human spaceflight relies entirely on rockets for transportation. Carrying astronauts to orbit, maintaining space stations, and returning crews safely to Earth all require rocket propulsion. Human presence in space supports scientific research, technology development, and international cooperation. Long-duration missions provide data on human physiology in space, informing future exploration planning. Rockets are central to planetary exploration. Robotic missions to the Moon, Mars, and other bodies require precise launch timing and high-energy trajectories that only rockets can provide. These missions have transformed understanding of the solar system by revealing planetary geology, atmospheres, magnetic fields, and potential habitability. Sample return missions depend on rockets for both outbound travel and return to Earth. National security considerations also make rockets strategically important. Launch vehicles are used to deploy reconnaissance, communication, and early warning satellites that support defense and security operations. Independent launch capability is therefore a priority for many nations, as reliance on external providers can limit access to critical space-based assets. Economic activity in space continues to grow, and rockets enable this expansion. Commercial satellite deployment, space-based services, and emerging industries depend on reliable launch access. Lower launch costs increase opportunities for research institutions, private companies, and smaller nations to participate in space activities. Rockets act as the gateway that makes space economically accessible. Rockets also play a role in planetary defense. Detecting and tracking near-Earth objects requires space-based observatories, and potential mitigation strategies would depend on rockets to deliver spacecraft for observation, deflection, or impact missions. While such scenarios are rare, rockets provide the only means to respond beyond Earth's atmosphere. Technological advancement is driven in part by rocket development. Rocket engineering pushes limits in materials science, propulsion, computing, and systems integration. Technologies developed for rockets often find applications in other industries, including energy systems, manufacturing, and medical devices. The challenges of rocketry accelerate innovation across multiple fields. International collaboration in space is enabled by rockets. Joint missions, shared space stations, and cooperative scientific programs depend on coordinated launch capabilities. Organizations such as NASA, European Space Agency, and other national agencies rely on rockets to support collaborative exploration and research efforts. Rockets also remain relevant because no alternative propulsion system can yet replace them for surface-to-orbit transport. Concepts such as space elevators, electromagnetic launch systems, and air-breathing spaceplanes face unresolved technical and economic barriers. Until such systems become viable, rockets remain the practical solution. In summary, rockets still matter because they underpin nearly every aspect of modern space activity. They enable communication, navigation, science, security, exploration, and economic growth. Their continued development reflects enduring needs rather than temporary trends. As long as access to space requires overcoming gravity with onboard propulsion, rockets will remain a foundational technology for humanity's presence beyond